Okay, so our next speaker is David Woodruff, who's at CMU in Google, and I think David needs a little introduction to many of us, but he's been one of the pioneers of doing like randomized linear algebra and like applying a lot of streaming techniques for major problems. So take it away, David.
Yeah, thanks very much for the organizers for inviting me. So the title of this talk is HyperAttention, Long Context Attention in Near Linear Time. This is joint work with Insoo Han, Raj Jairam, Amin Karbasi, Vaha Mirakni, and Amir Zandieh. So we've all been impressed with the ability of AI to generate realistic-looking images, to have interesting conversations with us, and even to create code for us. And at the heart of this AI revolution are what are called foundation models, and a common foundation model is what's called an autoregressive model. So in this model, you have a sequence of text being input. So let's say we have a sequence of words. Please write a story. These are fed into the autoregressive language model. And the model tries to predict the next word by regressing against previous words. Okay, so maybe if this is your input, then it might output the word children. It's trying to write a story. And this word then is output and appended to the sequence of words. And then the next word is regressed against this new sequence. Maybe the next word is played. Its output added to the sequence. And maybe the last word is football. Okay, so this is an autoregressive regressive language model. And one of the most powerful such models is the transformer. Before 2020, these were mostly used in natural language processing. But nowadays, besides text modalities, they're also used for audio, video, and many different combinations of these modalities. So what is the input-output behavior of a transformer? So here's an example where I have this sentence, write a Python code to generate web page. So the first thing you want to do with this is to tokenize it. So you want to create tokens, which could be characters or words or more than one word. There are lots of ways of doing that. Byte pair encoding is one way of doing that. So let's say that we've created a sequence of tokens, and we're going to have n tokens if we have, so n is going to denote the number of tokens. And then we're going to apply a token embedding. So we're going to embed these tokens into vectors. Okay, so we're going to get n vectors in each in r to the d. Okay, so you should think of the dimension d as being small, maybe something like 128. Then these n vectors are fed into this transformer. And the output is a sequence of n vectors. This is called the output embedding. And for each of these vectors, you want to create a probability distribution. One way of doing that is to take a softmax of the vector. This is a probability distribution on a dictionary of human understandable words. So one way of outputting tokens is to look at the word that has the largest probability, and that can be your next output token. So maybe in this case, you output import, numpy, and so on. Okay, so what's actually inside of a transformer? So it has many different modules. It has a layer normalization module, which is useful for having smooth gradients, generalization error, training faster. Has positional encoding. So unlike some of the earlier sequence models like recurrent neural networks, you actually have to put the positions into the embeddings. Has feed-forward neural network. Has other aspects to it. But what we're going to focus on, and what's arguably the most important layer, is what's called the self-attention layer. Okay, so this is designed specifically for sequence data, and it's actually the bottleneck in terms of time complexity, as I'll discuss. And sometimes you don't just have one of these. Maybe you have multiple layers, maybe multiple self-attentions. So that's what this capital L is. And you take the output of all of them, you combine them in some way, and that's how you get your output embedding. Okay, so as I said, we're going to focus on the self-attention layer. Let me just say a little bit what's going on in there. So there's an n by n matrix. Recall n is the number of tokens. It might be super large. This matrix is indexed by, the rows are indexed by tokens. The columns are also indexed by tokens, or more precisely, the embeddings of those tokens. And the entries of this matrix are called attention scores. And well, you should think of this as a correlation matrix. So you should think of two words that are similar or co-occurring as having a high attention score. So typically, the diagonal has very large entries. And here we see a large off-diagonal entry corresponding to Python encode because these words typically co-occur. And so there's some process which takes a matrix like this, does something to the input embeddings, and produces an output embedding. But when you look at this, you can already kind of see a quadratic time complexity, right? Writing such a matrix, which is n by n, is going to take n squared time. And so there's a lot of work on trying to accelerate the self-attention mechanism in transformers.
Sorry, David. So
Yeah.
Go back.
Yeah.
But in the entries of the matrix themselves depend on the embeddings, don't they?
Yeah, I'm going to describe more how this works. Okay, this is just a high-level picture. Yeah. So we'll get into the details of that. Yeah.
N is the context length?
N is the context length. Yeah. Okay, I'm going to use D for the dimension of these vectors, which I'm going to think of as very small, like 128 or so. Yeah, so for example, if you take the Bible, it has like 1 million tokens. And if you want to have this in your self-attention matrix, the fact that you have an n squared time complexity is really prohibitive. So there's a lot of work that goes into improving this. Going back to Sech's question, let me say a little bit more what's inside of the transformer. So in terms of time complexity, most of the modules are very fast. Okay, so I'm going to suppress dependencies on D. Maybe this is n squared times D. So D is something very small. I'm going to think of it as constant or logarithmic. So the layer normalization, that's typically order n time. The feed-forward network, order n time. And so the real bottleneck is this attention mechanism, which is n squared time. And let's look at the attention mechanism and look at how the embeddings work. So what is the input to this layer? So you have either from previous layers or just from the initial token embedding, you have some list of n vectors in R to the d. And I'm going to write this as a matrix X, which is n by d. And you've learned some small matrices, which I'm calling W superscript Q, W superscript K, W superscript V. Q, K, and V are for query, key, and value. This is borrowing from database nomenclature. These are small D by D matrices, okay, that you've learned, learnable parameters. And what you do is you take your matrix X and you multiply it by WQ, and you get what I'm going to call the query matrix Q, which is n by D. You also multiply it by WK, which might be a different matrix. You get what's called the key matrix K. And similarly, you get the V matrix V. Okay, you take these three n by D matrices and do the following. So you create a softmax matrix of QK transpose. So QK transpose is n by n. The inner dimension is the small d. And you perform softmax on it. So what does it mean? What is the ijth entry? So yeah, so softmax QK transpose ij. Well, what we do is we exponentiate the dot product of the ith query and the jth key, and we're applying softmax on the rows of this matrix. So I should normalize by the sum over all j prime of e to the qi dot kj prime. Okay, so when I do this, each of the rows has L1 norm 1. In fact, it's a probability distribution because after exponentiating, the entries are non-negative. I create this softmax matrix, and then I multiply it by V, which came from here, right? And when I do that multiplication, I get an n by d output. That's my output embedding. Okay, so let's just rewrite the softmax matrix a little bit differently so we can look at where the time complexity is large. So we can define this intermediate matrix A, which applies the exponential function entry-wise to the matrix Q times K transpose. Okay, so it's the ijth entry is this without the denominator. And then we look at the row sum, and this row sum is going to be the ith entry, the ith diagonal entry of a diagonal matrix D, and D inverse is going to have the reciprocal of that row sum. Okay, so when I multiply D inverse times A, I normalize the rows and I get my softmax. Okay, so I've written this as the attention mechanism, the attention matrix as D inverse times A times V. And we see that there are multiple sources of quadratic time here. One is, how do I form this matrix A? It seems like it's going to take n squared, or more precisely n squared d time. After forming that, I have to sum the entries in each of the rows. That seems like it takes n squared time. And then even this matrix product takes n squared d time, all naively. Okay, so yeah.
Typically expect the softmax to be sparse because only a few entries are important.
So yeah, we're going to discuss this at length in previous work that assumes things like this and so on. So yeah, here you go. So there's a lot of work that, because of this quadratic time, tries to deal with it in some way. And one way, as Sesh mentioned, is maybe you can assume some sparse structure on the attention matrix. And there is a lot of work that does that. Sometimes it holds in practice, sometimes it doesn't. There's also kernel methods that use random Fourier features to try to approximate this matrix A. There's work that uses tools from low-rank approximation, like Nystrom approximation, to try to approximate this matrix A. So there's a bunch of work out there that tries to improve the time complexity here. There's also some very nice lower bounds in this area due to Josh Ullman and Zhao Song, which I won't state it formally, but it says a high-quality entry-wise approximation of the attention matrix requires nearly quadratic time, assuming a standard complexity assumption, the strong exponential time hypothesis. Okay, so it's clear we're going to need to make assumptions, and a lot of works do make assumptions. And so we make assumptions, we prove bounds under those assumptions, and we try to justify them in practice. So a lot of the work that I've cited over here doesn't have end-to-end approximations on the attention matrix itself. I mean, there is some work that does. So under different assumptions, the Ullman and Song paper also has a work that it gives end-to-end guarantees. But for the most part, a lot of this work, it's only focused on approximating the matrix A as opposed to the entire attention matrix. It doesn't have the D inverse and the V there. What we'd like to do is we'd like to compute an approximate attention matrix. And we'd like it to, we can measure how good it is in terms of approximating the real attention matrix. And the way we're going to measure that is, say, through operator norm. Okay, so we'd like that operator norm difference to be small. And a lot of previous works, they also don't support what's called causal masking. So in earlier sequential models like recurrent neural networks, you don't need to explicitly enforce that present tokens don't depend on future tokens just because of the way the model is built. But in transformers, you actually have to explicitly enforce that. And one way of doing that is with causal masking. So we'd like a scheme that actually supports that. Okay, yeah.
You said what causal masking does for us, but what is it? How do you actually enforce that?
Yeah, so we're going to show how to do that later in the talk. Yeah. Okay, so what is our approach for accelerating the self-attention layer? So we have two parts. One is we'd like to approximate this diagonal entry, matrix D. And you can just write out what the entries are. They're just the row sums of this matrix A, which is the entry-wise exponential applied to QK transpose. That's one thing we'd like to do. And the other thing we'd like to do is we'd like to approximate the matrix product A times V, or more precisely, D inverse A times V. Okay, so these are the sort of the two ideas that we are going to use to try to achieve near linear time. So let's start with the second idea. And here we can use tools from randomized numerical linear algebra. So we'd like to approximate, let's say, the product A times V. How do you do that? Well, A times V, what is it? It's just a sum of outer products, right? The first column, outer product, the first row, plus the second column, outer product, the second row, and so on. So it's a sum of n outer products. And a natural way of trying to approximate that is, instead of computing all of the n outer products, what if I were to sample a small subset of those outer products and reweight them? Okay, so maybe I can, preserve the product in expectation and have good concentration. So that's what we're going to do. And let me just say one thing. So why is sampling so useful here? Well, it's because we don't actually have this matrix A in our hand, right? If we're going to sample a small subset of columns, then we only need to materialize A on that subset of columns that we actually sample. Okay, so it saves for forming A, and it also saves for the product. Now you might worry, well, how are you going to do the sampling? A natural thing might be to uniformly sample, but you can imagine that there are instances where that's bad, right? Where you have high variance. So then, you might worry, well, a better thing might be to sample according to the norms. Maybe I should sample an outer product proportional to the norm of this column and the norm of the corresponding row. And if we want to do that, then that's bad again, right? Because we don't know the norms of these columns. They're expensive to form. Okay, so a nice result in randomized linear algebra says that actually, if you just sample from the norms of one of the two matrices in the product, you can still get a good error guarantee. Meaning that the error guarantee is a standard one. It'll be the product. It'll be epsilon times the product of operator norms of the two matrices that you're trying to multiply. And you only need to sample from the squared norms of one of the matrices. So we can just sample from the squared row norms of V, which we have in our hand. It's a small matrix. We can easily compute these squared row norms. And so you can show that if you sample roughly m outer products, so the row and corresponding column, and just average and rescale those, then you can get a good approximation. Here, m turns out to be what's called the stable rank of the softmax matrix times d, which is small. Yeah.
Well, what is the scale of the entries of A? Like, are the vectors qi, kj like unit vectors?
Yeah, everything is scale invariant because the error we're going to get is epsilon times the product of the operator norms. Yeah. So you can sometimes So in the way I've written it here, these are like bounded. If you have larger norm for the exponential function, you can divide by root d and so on. Yeah. But the actual error guarantee from randomized linear algebra is scale invariant. Yeah.
So, you haven't talked about the entry-wise exponentiation.
Yeah.
But in some sense, wouldn't that be a problem? Because small changes in the entries could be large changes when you exponentiate.
Yeah. So that's exactly one of the sources of hardness for this problem. But it all I'm saying right now is that we can approximate this matrix product, and we can get error that's in terms of the operator norm of this times the operator norm of this. If there's some super large entry, recall that one thing that helps us is that in the softmax, the rows are renormalized to have norm 1. But it still might be hard to find large entries, and that's going to come up repeatedly in this talk. Yeah. So so hold on to that thought for a moment. So how many samples do I need to take here? Well, if we take, as I said, the stable rank of the softmax matrix, roughly number of samples, then that gives a good approximation. And in practice, you can observe that the stable rank is fairly small. So we have experiments that show that. and we have assumptions under which we can prove that, that I'll discuss when I discuss our theorem. Yeah. Yeah, stable rank. So the stable rank of a matrix, B, is the squared Frobenius norm divided by the squared operator norm. Okay, so if all the singular values were the same, this would just be the rank, and this is kind of a more robust version. If you have one large singular value, the stable rank is very small, close to constant.
And then in the hard instance, the paper you mentioned, this stable rank parameter does go to n.
So I'll discuss a hard instance on this slide. Yeah, you'll see it. Yeah, which is actually similar to hiding heavy entries, as you suggested. Okay, so good. So that's one thing that we're going to do, but that's not the. Oh yeah. So the fact that we're only reading a small number of columns again gives us linear time to form AS transpose. That's the subset of columns. And then we can do, we choose a subset of rows. We can do this matrix product quickly, like n times m times d time. Okay. The other aspect to this is trying to approximate this diagonal matrix. It's not enough just to approximate the matrix product. Now, how can we approximate this diagonal matrix? Well, let's look at the ith entry on the diagonal. Again, it's the sum of the entries in the ith row of this A matrix. And there's some nice earlier work of Zandia et al. That observes that you can actually use kernel density estimation techniques because this is nothing other than a kernel density estimation query. Those algorithms will give you super linear time, so maybe n to the 1.17 or so. And as far as I know, at least the ones we tried were not practical. So we take a different approach here. And here's how we're going to approximate the diagonal matrix. So we're going to, for each row, try to decompose it into a set of heavy entries, which we're going to find in some way, and the remaining light entries. Okay, so for each row, we'd like to estimate its norm so that we can renormalize it. And to do that, we need to know the values of the heavy entries, and we also need some estimator for the values of the light entries. Okay, there are various things you can do for the heavy entries. So what we did in the experiments and what I'll talk about later is using locality sensitive hashing. We also have a theorem for count sketch, but in the worst case, this can be hard without any assumptions, but I'll discuss our assumptions as we go. So for the moment, just think you have some oracle that returns these heavy entries. For the light elements, those are very easy to estimate their contribution, because if I uniformly sample a small number of columns, then on every row I get a small uniform sample, and I can estimate the contribution of the light elements from that sample. So yeah, so that's how we estimate the ith diagonal entry, contribution of heavy, plus an estimate to the contribution of light. Okay, so here's an informal version of our theorem. So it makes an assumption, and I'm going to discuss that assumption below, which is that the maximum squared column norm in the softmax matrix, softmax of QK transpose, is 1 over n to the 1 minus little o of 1. Okay, let me get back to that, what that means. And the other thing that the complexity depends on is the ratio of row norms in the A matrix, which is, again, E to the QK transpose, entry-wise, after removing the heavy elements. Okay, so we want the ratio of row norms to be close to 1, or we can tolerate n to the little of 1, and we don't want any column norm to be too large. If we have these properties, then we can output an approximate attention matrix in near linear time. Okay, d times n to the 1 plus little o of 1 time, with this operator norm guarantee that I've been alluding to. Okay, so the operator norm difference of our approximation and the true attention is at most epsilon times the product of operator norms of the softmax and the value matrix V. Let me say a little bit about these assumptions, what's going on here. So I want to stress that this column norm bound is non-trivial. So there's previous work that assumes bounded entries for Q and K transpose. And if you have all the entries of QK transpose, bounded by a small, but by a constant, then when you take the softmax, in fact, all the entries are going to be theta 1 over n. Okay, which means all the squared column norms are going to be about 1 over n. Okay, so bounded entries does imply our assumption. But our assumption is weaker than that because we do allow some entries, after normalization to be as large as roughly 1 over square root n. Okay, and I want to stress that this, this actually causes some complications for the estimating of the light elements because now you have elements in your softmax matrix which could be as small as 1 over n, but could also be as large as 1 over root n. And so uniformly sampling might miss some of these larger elements. And in fact, so in fact, we're not able to estimate the norms of all rows in the A matrix. But what we can show, because of these larger elements, what we can show is that for the rows for which we can't estimate their norm, in total, that's a small subset of bad rows that has small operator norm. And we're able to use that in our overall analysis of showing this statement. Yeah.
So, so the softmax QK transpose, it's the rows that are distributions, right?
That's right. Yeah.
Not the columns.
The rows. Yeah.
The rows are distributions.
Yeah.
And you're saying the column norm, the squared column. Okay.
Yeah, and I'm going to motivate. I'll have a picture on the next slide to help you. But we don't want the column to have all ones. For example, suppose the column is just all ones, right? Then it is all the rows are probability distributions. But that column has very large norm. We're going to disallow that, yeah.
So it's like you don't want to. So if I think of it as there are basically like n distributions.
Yeah.
You don't want to have some elements that are important in too many of them. Is that?
Yeah, you can think. Yeah, that's equivalent. Yeah, where important is quantified by this norm. Yeah. Yeah. Any other questions? Okay. We did look at this assumption on real data sets. So we looked at a vision transformer on ImageNet, and the squared column norms were all small and uniform. So the assumption was satisfied. We looked at ChatGLM2 on Long Beach data, and we found that there were a few columns that had large norm, but these were always the lexicographically first. Okay, so it was easy to separately handle these columns and still achieve this error guarantee. Yeah.
For the third bullet.
Yeah.
It satisfied this column norm thing. Did it also satisfy the bounded entry assumption?
I don't actually know for this. Yeah, I don't know for that experiment. Yeah, I don't actually know if we even checked it. Yeah, yeah. Okay, so yeah, so motivating the column norm assumption. Suppose your A matrix looks like this, right? So this is again entry-wise exponential applied to QK transpose. Suppose the first column is all n's, and all the other entries are 1, except for about half the rows have a randomly planted n somewhere. Okay, so this is related to the hard instance in the Ullman Song paper. So that's your A matrix. And what is the D matrix? So the diagonal entries should correspond to the row norms. So the first row norm here is 2n, or more precisely 2n minus 1. Let's call it 2n. This one is roughly 3n, and so on. Okay, so I either have a renormalization, which is, I either have a sum which is 2n or 3n for each row. And let's look at what the attention matrix is for a specific example and see what happens with our error guarantee. So when we look at the softmax matrix, we're going to apply D inverse to A. And so we're going to renormalize each row by either 1 over 2n or 1 over 3n. Okay? And so this first column that was all n's, for the rows that we didn't plant a random n somewhere, we're going to get 1/2 here. And for the rows that we did, we're going to get 1/3. Okay. And let's suppose that our value matrix V is just the first standard basis vector, okay, 1 and all zeros. Then the attention matrix is just the first column of the softmax matrix. This product is this column. And the claim is, with our error guarantees, we can recover most of these entries. So for most of these entries, we can figure out if they're a half or a third. Okay, and therefore, what that means is for most of the rows, in particular for a typical row, you can tell if you planted a random n somewhere or not. Why is that? You can show the softmax matrix has squared operator norm n. This V matrix has squared norm 1. And if you look at our error guarantee, the squared operator norm of the difference has to be at most the product of these two squared operator norms times epsilon. Let's say epsilon is 1/10. So we'd get at most n/10 here. And so what that means is, these two things are vectors, and they have to, be close on most entries, okay, in order to get this kind of error guarantee. And so you can solve this problem. And yeah, as I said, this problem is very related to the hard instance in the Allman Song paper, where they show a near quadratic lower bound. And the point of our column norm assumption is, we can avoid this instance, right? So this bounded column norms would completely avoid this instance. We wouldn't be allowed to have such a column here. Okay, so in the remaining time, let me just briefly say how we find the heavy hitters or the heavy contributions in practice. So we'd like a GPU-friendly algorithm for finding the heavy entries. And really what that means is we'd like to minimize I/O complexity. Okay, so that's really the bottleneck in these algorithms. We can do the matrix multiplications very quickly. And so what we'd like is some kind of algorithm which is able to permute the rows here, these the rows in Q, and also permute the columns here, the columns in K, so that after the permutations, the matrix roughly looks block diagonal. Not only does it look block diagonal, but we also want the blocks to have roughly all the same size. Okay, why do we want this? Well, with a GPU, what we could do is we could load these queries and these keys, and then we could quickly do a matrix multiplication to get all these heavy entries. Okay, so the fact that this is a block allows us to compute many heavy entries quickly. The fact that all these blocks have the same size allows us to do this all in parallel. We can run all these matrix multiplications, one for each block in parallel, and since they have the same size, they'll roughly finish at the same time. That's the idea here. So how can we find such permutations? So as I mentioned earlier, we're going to use a version of locality sensitive hashing to do this. So this is called sort LSH. And here's what we do. So we have all of our keys and queries. These are just points in R to the D, which I've drawn here. And what we end up applying in the experiments is we apply simhash. And for the purposes of this talk, just think of choosing a random vector and taking the dot product with that. Is it positive or negative? And if it's positive, then you get a 1. If it's negative, you get a 0. And so I take a bunch of random dot products, and I can write down my binary encoding under those dot products using that rule. So that's simhash. And we can look at the profile of one of the query vectors or key vectors, and maybe this is 1, 0, 0, 1, 0, 1, 1, 0, 1. That's its profile with respect to these random directions. And there's a bunch of queries and keys that might have the same profile. So those would all get hashed to the same hash bucket. And so what we'd like to do is this is why it's called sort LSH. We'd like to organize the queries and keys by hash bucket. Okay, so we'd like to list all the queries in the first hash bucket here and the corresponding keys in the first hash bucket here. Now, you might not have similar queries and keys going to exactly the same hash bucket. So another reason it's called sort LSH is you're going to sort these buckets by Hamming distance. Okay, so if you have, here is another bucket where if you look at the profile, this string, sorry, I guess I should stop soon, but if you look at this string, then the Hamming distance is just 1 here. Okay, and the Hamming distance of this string to this is 1. So you might want to put these in order. Okay, so you'd have all of these queries, followed by the queries here, followed by the queries here, and similarly for the keys. Okay, so yeah, that's what we do, and we get a roughly block diagonal matrix in practice with similar sized blocks. And yeah, so let me just wrap up with one other loose end, which is Jelani asked about causal masking earlier. So in causal masking, you don't want past tokens to attend to future tokens. So you typically zero out everything above the diagonal in the matrix A, this E to the QK transpose. You can write that as taking the Hadamard product with a mask matrix, which zeroes these out and keeps these preserved. And one way of solving this heuristically, we don't have a proof for this, is just to do a simple divide and conquer approach. So we can break this into 4 matrices of size n/2 by n/2. This matrix is all zeros. This is a smaller instance of causal masking. This is a smaller instance of causal masking, and this is what we already know how to solve. It's attention without causal masking. But yeah, we don't know if our assumptions hold recursively. This is something that we should check in practice. And yeah, I can just say one slide about the experiments. So there are assumptions here, but the experiments are quite promising. So for example, we took ChatGLM2 and we took data sets from Longbench with a context length of roughly 32,000. And what did we do? Well, it turns out the first few layers in ChatGLM2 are very important. So what we did is we started replacing layers from the end. Okay, if we replaced 0 layers, and what does it mean to replace a layer? It means to take the n squared time attention matrix and replace it with our near linear time. If we replace 0, then the error, which is measured in terms of what's called the perplexity of the output distribution, is actually just 2 to the Shannon entropy of the output distribution. You want the entropy of the output distribution to be small because you want to decisively choose some word. So the perplexity was between 5 and 6 here. And as we replace more and more layers from the end, the perplexity didn't grow too much, but the speedup was significant. So for example, if we replace 16 layers, we got a speedup of maybe 1.6 and a perplexity 6.4 or so, which wasn't too big of a change over the original perplexity. So yeah, so it's ongoing how to optimize this in practice, and let me just stop there. Thanks. Yeah. Oh yeah.
If I understood you correctly in the beginning of the talk, you said that the bottleneck is those attention computations, which are quadratic, right, and this approximation is near linear.
Right.
So why are the speedups bounded by 1.5?
Why are they bounded by 1.5? Okay, so there's a lot of stuff that goes into this. I mean, there's like we measured speedups with forward and forward plus backward propagation with and without causal masking. I don't remember exactly where this plot comes from. Vahab, do you?
So yeah, if you only look at that attention layer, you get much more speedup. This is like the end-to-end speedup, including the feed-forward layers, and there's a lot of jargon around this. And like actually, majority of the memory and the thing like for 32K goes to those. So this is like good given the fraction of attention, like the time that we spend on attention computation.
But does that mean that in the end, the attention computations are only a constant fraction of the running time and not the vast
So
majority?
as you increase the context length,
Yeah.
that fraction increases. So at the moment, it's like less than half. So like the speed up for attention is much more. Like if you look at the paper, like it's like 10x or more. But then when you look at the end-to-end, you get this much speed up. That.
Any other question? Let's thank David.